All right, the integral test. In this chapter, we're talking about sequences and series. So, with respect to sequences and series and calculus, what are we interested? What are we trying to find? Does it converge? That's the question we have to answer. Because if it converges, what does that mean to us? But what does that mean? What does that ultimately tell us? What good is that going to be? Well, it could go on forever, but it's approaching a value. But what we're doing here is looking at if it's converging to a number in engineering, in the real world, we're looking at, okay, at what point will this metal break? So that's what so we have the temperance values as zones. So at what point, so what's the converging point? At what point will the stress be so much that it's going to snap? Or at what degree what temperature will this thing stop working, or will it penetrate through the whole shield? So this is how it is in the real world. This is how we know you have a sequence of numbers, the data points, see what happens to it. That's what we're going to do here. And we talk about partial sums. What's a partial sum? Partial sum is if we have a sequence, each of these values for example, the partial sum of the first element of the first round is A1. The partial sum of the second is A1 plus A2. And the third partial sum is A1 plus A2 plus A3, all the way down to AN, or S sub n. Now, if it converges, there's no real formula that tells us what it is. We look at with the sequence, does it converge? Does it tell us what number it converges to? Not really. That we have to do something else. To find the estimated sum of a convergent series, we look at the errors involved when using partial sums. As approximation tools. We talked about also recap. What is a monotonic sequence? Or when we say monotonic, what does that mean? We talked about it last class. And if you weren't here last time, here's some worksheets here. Monotonic means one of two things. It's non-increasing or non-decreasing. And it's bounded. So if a sequence A sub n is bounded and positive, then the sequence converges. We talked about monotonic sequences in section 1, I believe. So what does it mean by being bounded? Well, it means that there's either an upper bound, which the function doesn't exceed, or a lower bound, or a lower bound where it doesn't exceed there either. It stays between there. It's bounded. It's like a borders. So there's a corollary to the monotonic sequence theorem. Corollary to the monotonic sequence theorem. It says this. A series n equals 1 to infinity of a sub n of non-negative terms converges if and only if, which from now on I'll write IFF. Its partial sums are bounded from above. Why bounded from above? The answer is inside that statement. Yeah, because it says non-negative terms. So it's bounded above, and the lower bound is the x-axis. Very good. Good catch. So here's an example. Example 1. As an application of the above corollary, consider the harmonic sequence n equals 1 to infinity of 1 over n. If we were to write the first terms, what would that look like? First, when n is 1, it's 1 over 1, which is 1. Then 1 over 2, then 1 over 3, 1 over 4, dot, 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 to 1 over n, and then keep on going to 1 over infinity. Okay, consider this application. As an application, consider this harmonic. Although the first nth terms the nth term, 1 over n, does not go to 0, the series diverges because there is no upper bound. For the partial sums. How do we know there's no upper bound? Remember, because there's no upper bound, for the partial sums. Remember, partial sums, let's look at this sequence. So we have 1 over n. It becomes 1 plus 1/2 plus 1/3 plus 1/4, 1/5, 1/6, 1/7, 1/8, and so on and so forth. If there was an upper bound, could this function, that means this function would stop growing. But what's happening here? We start off at 1. And we add 1/2. That's 2.5. Now, if we look at the next set, 2 terms, 4 terms, and then 8 terms, and then 16 terms. What happens to those? So we start off with 1, then we add 1/2. Is this next number going to be bigger than or less than 1/2? Is it going to be bigger than or less than 1/2? Let's look at this thing. Compare this one. If it was 1/4 plus 1/4, what would that equal? That would be 2 over 4, makes it 1/2. Okay, so this window is 1/2. 1/4 and 1/4 are equal. Is 1/4 bigger than or less than 1/3? 1/3 bigger than or less than 1/4? 1/3 is bigger. So this number is bigger than this number, which is 1/2. So it goes 1 plus 1/2. Now this is bigger than 1/2. How about this next sequence? What if we had 1/8 plus 1/8 plus 1/8 plus 1/8? What would that equal? 4 over 8, which is 1/2. Now compare them. 1/8 to 1/8, that's equal. Is 1/7 bigger than or less than 1/8? It's bigger. This one's bigger. So this sequence is bigger than this sequence. So this sequence is greater than 1/2. This sequence is greater than 1/2. The next one with 8 terms, it'd be 1 over 16, 1 over 16, 1 over 16. Each term is bigger, so this part is bigger than 1/2. So what's happening to these numbers, these sequence of numbers? They're getting bigger and bigger and bigger. Because they're going to infinity, that means it diverges. If it was converging, it would be going down to a number, going down to 0. So let's look at some examples here. Well, besides that one. Ooh. So the first thing we're going to talk about, the integral test. Let's recap what we talked about here. What does an integral find for us? Area under a curve. So we're going to refer here to areas under a curve and how it relates to what we're looking for here. So example 2, and we'll talk about this in a second. Does the following series converge? So we have summation of n equals 1 to infinity of 1 over n squared. So that's going to equal 1/1, which is 1. At 2, it's 1/4. At 3, it's 1/9. 1, it's 1, at 4, it's 1/16. 1/25, and then so on and so forth to 1/n squared, because it's squared, and then all the way to infinity. So does it converge or does it diverge? Well, let's see. We can't just look at bad stuff. We have to look at the terms themselves. What about the series 1/x squared? Not the integral, but from a to b of 1/x squared dx. We're going from 1 to infinity, so a is 1, b is infinity. What about that? But remember, we're going to use an integral test here. Let's compare this sequence to this sequence. What happens with this one? Does that one converge or diverge? It converges because as we go from 1 to infinity, as x goes from 1 to infinity, this number goes down to 0. So we know it converges. So let's look at the numbers. Let's look at the partial sums. The partial sums are made up of 1/1 squared, 1/2 squared, 1/3 squared, and so on and so forth to 1/n squared. So that's the partial sum of these guys here, which is 1 plus 1/4 plus 1/9 ... 1/n squared. So comparing the two, our sequence and our function, 1/x squared. This is the same as f at 1. This is the same as f at 2, f at 3, and this is f at n. So now, what does this stuff tell us? What does this find for us? Integral finds area under the curve. So if we look at our graph, what does 1/x squared look like from 1 to infinity? The function 1/x squared looks like this from algebra. I know if x squared is like this, the Atari symbol. 1/x is this, 1/x squared is that. We're only going for the positive side. So what we're looking at here, when x is 1, when x is 2, when x is 3, when x is 4, when x is 5. So what do each of these represent? Each of these represent areas. So this is from 0 to 1. This is 1/1 squared. From 1 to 2, 1/2 squared. 1/3 squared, 1/4 squared, and so on and so forth. Follow me so far? So now, how do these two relate? Can we rewrite those as a sequence, as an integral? Can we rewrite those as a sequence? Because remember, since we're looking for areas under the curve, the areas represent the Riemann sum, which is the integral. So that is, we start off with the first one. 1 to n. Our function is 1 over x squared. What is f of 1? 1. Remember, the function is 1 over x squared. So f at 1 is 1. Integrate 1 over x squared becomes the integral of x to the power -2 from 1 to n. The integral of that one is n -2 plus 1 over -2 plus 1 from 1 to n. -2 plus 1 is -1, n to the -1, -1, which is -1 over n. I'm going from 1 to n because that's just finite number there. Plus, so this one, let's see, so it's, I need more space. So I have 1 plus n to the -1, so it's -1 over n from 1 to n. And x. Good. So this is x. So I got -1 over n minus -1 over 1. 1 minus 1 over n plus 1. As n goes to infinity, take the limit of it, we get 1 plus 1 equals 2. So the sum of our partial sequences, so S of n equals 2. Converges. So how do we know it's going to converge? Because if we looked at this graph, is it bounded by above? Yeah, it's bounded above by this function. It doesn't keep on going to infinity. It's being taper down. It's got an upper bound. It can't go any further. And the lower bound is the x-axis. So let's define what the integral test really is. The integral test. Actually, before I move, any question? I mean, did I go too fast for you on the first one? Because look, you have to look what we just did here. We looked at the sequence, we worked it out from 1 to n. Because what we're doing here, we're comparing this sequence with this integral. So we have that for our sequence. That's our sequence of values. But now our integral at 1 to 1 is 1, 2. But remember, integrals finds the area, and that's what we're looking at here. So we're seeing as the area keeps on going, where does it stop? It stops at 2. Well, yeah, the 1 over n goes to 0, eventually tapers off. So the area from 1 to n, the area is 2. From between that area, between 1 and n. And that's what we just figured out with using this. All right, so the integral test says this. Let the sequence a sub n be a sequence of positive terms. Well, remember, when we talked about it earlier, we said it had to be non-negative values. So it is. So we're stating that again. It's got to be a sequence of positive terms. Then suppose that a sub n is equal to the function at n, where f is a continuous non-negative decreasing function of x for all x bigger than some value n, where n is some positive integer. Okay, let's look at this so far. The integral test. Let the sequence A be a sequence of positive terms such that a sub n equals f of n. Does that relate with what we just did? Yes. What we just did, these are my sequences. This is a sub n. So here's a sub n, a sub 1, a sub 2, a sub 3. It matches to f of 1, f of 2, f of 3. So a sub 1, a sub 2, a sub 3. So that's the relationship there. A sub n equals f of n. Now, why does A have to be continuous? If it wasn't continuous on that domain, if there's a hole, then that domain just goes to infinity. There's no limit to it. So it's got to be continuous, non-negative. Why non-negative? It's got to be above the x-axis. So we're only looking for an upper bound. Decreasing. Why decreasing? We want it to converge, right? So it's got to be continuous, non-negative, decreasing function of x for all x's greater than or equal to some value n. So any n you give me. So let's see. Where did I leave off? That. Then the series summation of n equals capital N to infinity of a sub n and the integral n to infinity of f of x dx, both either converge or diverge. Why is that true? Yeah, because of this basic factor here. If the sequence a sub n converges, then the function converges. If it diverges, it diverges because they're a one-to-one relationship. Yeah, or we could look at that the integral from 1 to n plus 1 of f of x dx is less than the sequence, which is less than or equal to the integral 1 to n of f of x dx. Let's look at another example. Example 3. Show that the P series, which is n equals 1 to infinity of 1 over n to the P, or real constant number, show that the P series converges if P is greater than 1 and diverges if P is less than equal to 1. So let's look at the first one. Well, first off, this P series, P is any constant. In the other examples we had 1 over n squared. So P equals 2. What happened when we had 1 over n squared? Did it converge or diverge? We just did that last example. It converges. So what are we saying here? So we're saying that this one's going to converge. Or we're hoping it's going to converge if we do it right. So here's our solution. If P is greater than 1, then what do we know? Well, then what does f of x equal? Because we have to have, remember, a sub n has to equal f of n, according to our theorem. So if p is greater than 1, then f of x equals 1 over x to the p. Remember, p is a constant. The only thing that changes is the x. What do we know about this? Then is it positive? Are there any negative numbers here? No, because remember, p is positive. X goes from 1 to infinity. So it's positive. Is it increasing or decreasing? This number? 1 over x. As x goes further, what's happening? It's decreasing. Okay, so f of x is a positive decreasing function of my variable x. Why is that important? Let's look at the theorem. Suppose that a sub n equals f sub n, where f is a continuous, non-negative, decreasing function of x. So we have to match those conditions. So it's positive, it's non-negative, it's decreasing because this value gets bigger and bigger and bigger, and it's a function of x. So check. So we can go from 1 to infinity of our function f of x dx, which is equal to 1 to infinity, 1 over x to the p dx. So let's do the integral. How can we rewrite this? How can we rewrite that? X to the negative p. What's the integral going to be? X to the negative p plus 1 divided by negative p plus 1 from 1 to infinity. What's that? Here, yeah, plus 1. But remember, to find the sum using the integrals, we also now have to look at taking the limit as b goes to infinity of our function x to the power negative p plus 1 over negative p plus 1 from 1 to some value b. Why did we do that? Because remember, what is n or x? X is bigger than some value of n. So we're going from n equals n to infinity, n to infinity. So we're changing the bound. So we're going from 1 to, instead of n, we're going from 1 to b. Why? Because b has to go to infinity. What does that do? It makes this the value smaller. Okay, so what do we do here? Is there a constant here? Remember, p is a constant. So we have 1 over negative p plus 1 is the same thing as 1 minus p. It makes it much easier to write that. So then I have the limit as b goes to infinity of x to the power negative p plus 1 from 1 to b. Put that on the other side. Equals 1 over 1 minus p. The limit as b goes to infinity of x to the power negative p plus 1 from 1 to b. So let's look at this part here. So we have 1 over 1 minus p. The limit as b goes to infinity. This one is b to the power negative p plus 1 minus 1 to the power negative p plus 1. P. Let's look at this. Let's rewrite our equation. We know this part here. What is that going to equal? Remember, P is a constant. What does this become? -1. 1 to any power is always 1. So this one here can be rewritten how? Remember, this one is a negative. If we take out the negative, we have P minus 1. So it becomes 1 over B P minus 1. We can, as a negative exponent. Why is that important? Because as B goes to infinity, what happens? Limit. As B goes to infinity, what happens inside here? B goes to 0. So we have 1 over 1 minus P, 0 minus 1 is equal to -1, 1 minus P. So it converges. Okay, okay. This is not the value it converges to. This is not the value. This is the sum of the series. Is that equals, as we started off, it just tells us that since this is a finite number, it converges. So that was when P was greater than 1. Now we have to look at first part. So the first part, it converges. What happens if it's less than 1? Part B. If P is less than or equal to 1. I don't need that anymore. What happens here? So what do you think is going to happen here? What's going to happen to the sequence? If it's less than 1, are there any conditions on P? Can't be negative. It's going to be a fraction, right? So since greater than 1 converges, then this one's going to diverge, because instead of going to 0, it's going to go to some bigger value. Well, because it says less than or equal to 1. What happens when it equals to 1? Have we seen that equation before? Summation as n goes from 1 to infinity of 1 over n to the power p. So if p equals 1, we have 1 over n. We just did that one earlier. This is the one that goes 1 plus 1/2 plus 1/3 plus 1/4. And we saw that each of these are bigger than 1/2. Then the next 4 was bigger than 1/2. So they kept on going, so it diverged. So if it's less than or equal to, since it's equal to, it diverges, then less than it diverges for the same reasoning. Because each of these terms, when I add them together in sequence, it becomes bigger than the previous term. But as you can see, what happens here in a harmonic sequence, it grows very slowly. Very, 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 very slowly, because it's just very, very minute changes. Example 4. The series summation of n equals 1 to infinity of 1 over n squared minus 1 is not a p-series. Why is it not a p-series? A p-series is 1 over n to a constant. Does this one have an exponent? No. And p is not equal to, if equals 1, then so this is just equals 1. So it's not a p-series. It's just a regular function. So does it diverge or converge? So let's see. Is our function f of x 1 over x squared minus 1? Should be plus 1, sorry. Is it positive? Remember, n's got to be bigger than, equal to, or bigger than 1. This is 1 plus. So can it be negative? No. So it's positive. Is it continuous? Yes, because there are no asymptotes here. The bottom can't be equal to 0. And the third condition, is it decreasing? As x gets bigger, does it get smaller? So those are all part of the conditions that we had to talk about. So the function, so f of x is positive, continuous, and decreasing on all x's bigger than equal to 1. Because that's what we're starting off with. Now, because that's so, we can look at the function integral from 1 to infinity of 1 over x squared plus 1 dx. And that equals to the limit as b goes to infinity of our integral 1 to infinity 1 over x squared plus 1 dx. But this one goes from 1, instead of infinity now, it goes to 1 to b. That's the transformation we have to do, because we're going from 1 to infinity. It's going to be this, it's going to be the sum, which is the Riemann sum of the limit from b goes to infinity of this integral. So we have the limit as b goes to infinity. What's the integral of the function? 1 over x squared plus 1.
Arctangent.
Arctant, yes. Arctangent of x from 1 to b. That's in the cheat sheet. You should always have your cheat sheets next to you, because these are going to pop up now everywhere. So we have the limit as b goes to infinity from arctangent b minus arctangent 1. Now, as b goes to infinity, what does the graph of the arctangent look like? So as b goes to infinity, so we have here the limit as b goes to infinity of arctangent b minus the limit as b goes to infinity of arctangent 1. So it's like the inverse function. At what point does arctangent go to infinity? The tangent function goes to infinity at pi over 2. Remember, the tangent function looks like this. There are asymptotes at pi over 2, negative pi over 2. So it goes to infinity when it gets closer to pi over 2. So arctangent at infinity is at pi over 2. Whereas at what angle does the tangent equal to 1? Remember, tangent is sine over cosine. Where are sine over cosine the same value?
Pi over 4.
Pi over 4 at 45 degrees. So we have 2 pi over 4 minus pi over 4 makes it pi over 4. That's our solution. That's not our area. It just tells us that it converges. Remember, the integral test doesn't tell us the value it converges to, it just tells whether it converges or not. Arctangent is simply another way of writing inverse tangent. So we're looking at where is the tangent, what's the angle where tangent goes to infinity? What's the angle where tangent becomes 1? That's what it's asking. We have to work backwards in the arctangents. Arcsine, arctangent are the arcfunctions. Example 5. Determine the convergence or divergence of the summation of n equals 1 to infinity of n e to the negative n squared. Summation n goes from 1 to infinity of 1 over 2 natural log of n. Getting pretty close. Let's look at both of these separately. So obviously we're going to use the integral test, but that's what this section is all about. So how do we set it up? If we use the integral test, what are my bounds? From 1 to infinity. Let's see. Instead of n, remember our integrals are with respect to x. So we have to change from n, we have to change it to x somehow. So let's look what this equation looks like. It looks like n e to the power n squared. So as we change from n to x, it becomes x e to the power x squared dx. Using substitution, what's my u going to be? It's going to be x squared. So we have to find du. The derivative of x squared is 2x. Because what I did there, I changed it from u. I need to have du on top. Du is 2x dx. I have x dx. What am I missing? A 2. So I put a 2 there. I got to put a 1/2 out in front. So it's du. This is just the limit part. I mean, now that's just the integral part. Now we have to take the limit as b goes to infinity of 1/2, 1 to b of e to the power negative u du. It's a constant multiple. I can put that on the very front. So the limit as b goes to infinity. What's the integral of e to the power negative u? E to the negative u plus 1, negative u plus 1. No, that's an equation. I'm sorry. The derivative of e to the power u, or the integral of e to the power u is eu du. So all we're missing here is a negative. Remember, the derivative of EU is EU du. So the integral of EU is EU du. So we have negative e to the b minus e to the 1. So this becomes 1/2. The limit as b goes to infinity of that's still a negative. So it's negative 1 over e to the b. Yeah, that still says negative. And so it's e to the b minus a negative 1 over e. Because this one is going to be negative e, be negative 1 over e to the u, which is negative 1 over e to the b minus negative e to the 1. Negative 1 over e to the b plus 1 over e As b goes to infinity, what happens? As b goes to infinity, what happens to e to the b? It goes to 0 because e is 2.7. As b goes to infinity, that goes to 0. So we're left with 1/2 1 over e, which makes it 1 over 2e. So it converges. Here's the second one. Summation of 2 to the power ln n, or is it ln x? Ln n. Yeah, we have to change it to x. We have to change n to x for our integral. So we have integral from 1 to infinity. So we have to use substitution. That's going to be u is ln n. Du is 1 over n. Oh. So that becomes 1 over 2 to the u dx. Yes. I was looking at this one for a second. So if that's going to be u is ln. What's dx going to be? So x is going to be 2u du dx. Oh, so first thing you have to do is make it 2 ln x. So that's ln x. So du is going to be 1 over x dx. So dx is equal to du times x. And x is equal to, so we have u equals ln x. Take the e to both sides, so we have e to the power u equals x. So that gives us 1 to infinity, 1 over 2u du eu. So we'll just set that up to eu du over 2 to the power u. Okay, now here's the part I forgot. So when you change it from this to this, we converted that so it's ln x. So my u value is u is equal to ln x. It got to be integral dx. So what's the derivative of u is 1 over x dx. Dx is equal to, then dx is equal to, so in place of x, I put du times x. So in place of that, I put that. And what is x? Well, I go back up here and I solve for x. I take the e of both sides. I get e to the power u equals x. So in place of x, I put eu. All right. So now my equation can look like e over 2 to the power u du. Now I have a rational expression. Take the limit as b goes to infinity. Of the integral from 1 to infinity, e over 2u du. The limit as b goes to infinity. What's the integral of eu? What's the integral of eu? So this is the integral of this one is e to the power 2 times we have eu over 2 from 1 to b. The limit as b goes to infinity of 1 over ln e over 2 becomes e over 2b minus e over 2 1. That's going to be a problem. Ah, okay, here's the problem. My bounds of integration. What's the domain of ln? Can ln ever have 1? Can you take the ln of 1? No. So it's got to be, because the function looks like this. So we're going to take it from 0 to infinity. So it's going to be e to the 0. So we have the limit as b goes to infinity of 1 over ln e over 2, e over 2b. Anything to the power 1 is 0, is 1. So I have 1 over ln e over 2. That's a constant. Now, as b goes to infinity, what happens to this number? As b goes to infinity, it goes, since it's an exponent, e over 2 is a constant number. As the exponent gets bigger, it's a bigger, 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 so it goes to infinity. So anything times infinity is infinity. So it diverges. That'll work, but I had to make sure that I was going in the right bounds. My bounds of integration. Okay, should we do the error estimate? No, if we need it, I'll go over it next week, but I don't think we need it just yet.